All right. Hello, namaste, and welcome everyone. I hope I am audible. In case I am not audible, you can always unmute yourself and let me know if there is some issue with my voice or if something is not. I'm sharing my tab, and if it is not visible at any point of time, you can inform me.
Yes, you
Okay.
you are audible.
Thanks.
Thank you.
Okay. So let's get started. In this problem solving session, we will be discussing week 10 in particular. So uh, let me write that down. So this is week 10, and this week was mostly based on uh, convolutional neural networks. Yeah. So, basically, this week we basically scratched the surface of CNNs. Okay, so in short, these are called CNNs. Okay, so I will be using CNNs and convolutional neural networks interchangeably. We basically scratched the surface of CNNs. So the you know, uh, uh, basic idea of convolutional neural network was so what was the broad question that we tried to answer, so the broad question was, how do we handle uh, uh, data sets, yeah, uh, uh, which have with data sets which have spatial structure, or you can also call it local structure, yeah. So any one of these. So this was the basic, a question that motivates us to actually go towards CNNs. So what do we mean? So what is this question actually asking us, right? So basically, till now, what we have seen till now, we have seen feed forward networks, yeah, and in feed forward. So if you ask me, what did feed forward networks did was, it basically told us, a very straightforward way to I mean how to handle it basically described a straightforward way to handle vectors as inputs. Okay, so if your data sets are, a bunch of vectors which are, let's say, in Rn, you know how do we handle such vectors was the question, and feed forward networks were a good answer to that question. However, then we saw something. We came to, something called natural language processing, natural language processing, in which we basically asked ourselves that, okay, fine, feed forward networks are good, but how do we handle, languages? Basically, languages are a bunch of words, a sequence, right? So how do we handle sequences? That was the basic question in NLP. And the answer to that question came in the form of, something called representation learning. So we basically said that, okay, uh, representation learning, we basically said that, okay, fine, words are something which is a human construct, and we humans have made it for, our sake of understanding, but it need not necessarily imply that, it is easier for the words that we use are easier for the machines to learn, and stuff like that. So to overcome those problems, we came up with, different techniques, or different we saw different methods, how we can come up with representations of words, and we saw some supervised and unsupervised methods of doing that, and we saw pros and cons of each of them, and we saw that, in some settings, some of them are equivalent and stuff like that. So that was previous week's uh, uh, previous week's content. So this that was representation learning. Basically, we wanted to learn a representation for words, which we can directly use in a neural network to do some sort of classification or whatever our downstream task is. However, just a word of caution, uh, like there is much more than representation learning to NLP. Specifically, I think it will be there in one of the weeks where you will learn about special structures. For example, CNNs are special structures for images. In a similar manner, there are special structures or special networks that are used to handle languages. In particular, you will see something like LSTMs, uh, GRUs, RNNs. So, so the question there will still remain the same. In particular, we will ask some a question that is similar to this one. However, this thing will change, right? Uh, the question will be how do we handle sequenced data, right? All right. So, so this was last week's content, right? However, now when we come to image image processing, image processing. Uh, so the first question that comes to our mind is what do we even mean by an image is the first question. So to answer that, a generic answer is that images. If you start with if you take a black and white image, right? Black and white image is just a matrix, which is let's say R n cross n. What do we mean by that? So we are saying that okay, uh, there are n rows, so its height is n, and it has m columns, so it has it has a width of m, and so it is basically a matrix, and each element of of this matrix is what we call a pixel, right? And more specifically, so it will be a particular pixel here is like Pij, I comma jth element of this matrix is a pixel, right? And there is some constraint on Pij. In particular, Pij can only take values between what 0, 1, 2 till 255. Okay, so this is what we call as so what is I mean, so if you want to even go in further details as to why it can take only these values, I would suggest you to look up on Google. In particular, there are some mechanisms that are involved when you capture a image. Okay, it's not so. For example, you are using a camera, let's say, and you are capturing something. Uh, there is some underlying mechanism that goes into capturing that particular image. That mechanism enforces your uh, image to have values in the uh, enforces your image to take values from this set. Okay, so this was for black and white image. If you take your general RGB image, which has three channels, RGB image, right? That is it is not a so so it is not a vector like this. It is not an Rn vector. It is neither. It is a matrix like Rn cross n. In fact, so the word that is generally used for something which is above two dimension is what we call as tensors, right? So it is something called let's say width cross height cross channel. Okay, what does it mean? So it means that okay, it has some height and width, okay, but apart from that, it also has some depth to it, okay, something like this, right? And that depth, this depth or is what we call as number of channels, okay. So this is C, this is your width, okay, and this is your height. So an image that we see in our daily life is actually an RGB image, and it has three dimensions. The first dimension is your width, another is height, and the third one is a channel. right? So in an RGB image, the number of channels is actually three. So there are three channels in your image. Uh, so the what are these three channels? Each of them are as follows. One is an channel representing the red spectra. Another channel is a blue. Another channel represents blue spectra, and the third channel represents green spectra, right? So R, G, and B. This is why we call it RGB image, because it contains three channels. Each channel shows one of the corresponding spectra. Okay, and so let's say if if I have to index a particular pixel in an RGB image. Okay, so if I have to index a particular pixel in an RG image, I will require three coordinates. I hope you will agree with me on that. So if P is a pixel, I will require I, J, and let's say some kth coordinate as well, right? So we require three coordinates. Now again, as was the case with black and white images, RGB images also follow the same rule. I, J, K have to belong from zero from this set 0, 1, 2 till 255. Yeah. All right. So this was, just some background on what are images and how do we actually deal with images and stuff like that. If you want to go in details of this, I would suggest, there is if you want to go in details of this, I would suggest you to watch. You can see this, a very good lecture series by Professor uh, Vineet Balasubramanian. I hope I have written his spelling correctly. He is a professor at IIT Hyderabad. So he has a playlist on NPTEL or on YouTube, which titled Image Processing. Uh, in the initial lectures of that playlist, you can find the details of how an image is captured and what actually is a pixel and stuff like that. Okay, all right. So having said that, uh, the next question that we would like to ask ourselves is, uh, why why do we why do we need to go towards something like convolutional neural networks and stuff like that? So if I were you, one thing that would come to my mind is, till now we have built all our arsenal, all our machinery based on something called feed forward networks, right? And suddenly someone is now saying that, okay, feed forward networks are not enough. We need to go towards something called convolutional neural networks, CNNs. So my first question would be, why should we, have this shift in paradigm? Well, to have to explain that, maybe we can take an example. So suppose this is an image. Okay, sorry. All right. So let us say this is some image. I'm not considering the channel dimension for now, but things will generalize to channel dimension. It's not a big deal. So let us say this is an image. Okay. So so there are some inductive biases that I have towards an image, right? I have some concepts that I would like my network to accommodate uh, while I'm training it. So what are my inductive biases? So let me write those things. Inductive biases. First of all, the first thing that I would like this network to take into account is some spatial structure. What do I mean by that? Well, consider this, right? Let's say that so maybe this is a tree. Okay, I'm not good with drawing, but okay. let's say, this is some tree, something like that. Uh, I hope you will agree that, if I, so suppose this is, this is the bush of the tree. Okay. If I take a, if I, so let me zoom in. Okay. Okay. So something like this, and yeah. So if I take a pixel here, okay. So this is one pixel. So if I ask you the question that, okay, so let me look at the surrounding pixels as well. Okay. So these are the surrounding pixels. Okay. And I ask you this question that, okay, so this is the my pixel that is under considerations. Okay. And these are the surrounding pixels. Okay. So my question is that, are the surrounding pixels, so are these green pixels somehow related to the blue pixel that is there in the middle? So I hope that it's intuitive enough, and you will agree with me that, in an image, a pixel is definitely related to its neighborhood pixels. Okay. What do I mean by that? That I mean that, this pixel gives me some information about what the surrounding pixels will look like. For example, if this is a tree, and this pixel, is, let's say, has a, is, let's say, green. Okay. It tells me, if you show me that, okay, uh if someone does this experiment with me, he says that, okay, what I will do is I will mask these pixels. Okay. The surrounding pixels, I will just mask these pixels, and I will only show you the middle pixel, that is this one. And the question you pose to me is that, okay, I have shown you this pixel, I have masked these other pixels that were there in the neighborhood. Can you tell me what were the masked pixel actually? Well, I mean, being a human, and, I have some inductive biases. I see pixels around me and stuff like that. I will say that, okay, fine. This is a green pixel, and I can see that, this is a tree. So hopefully, if this is green, these pixels should also be green. Okay. So this is some information that is somehow built in my brain, and, I would like my network to, perform operations that is similar to this. Okay. So if that is the case, so that is what I mean by, taking into account the spatial structure, right? Other thing, so this is the major, so this is like, this is, let me make a star around it. So this is the major motivation for using CNNs. Okay. Another thing, if you ask me, that I would like my network to take into account, would be something called, invariance. What do I mean by invariance, right? So let's say, I am doing some sort of classification problem of, okay, if there is a tree or not. Okay. Now what I do is the following. Okay, I take this image, I take this big image, whatever it is, copy it, and I make another image, paste it, and what I will do this time is, I will just rotate it, right? So what I have done is, I have taken the same image, and I have rotated it by some angle. So let's say this is, so this was the original axis, and I have rotated the image by this angle. Okay. Now the question is, now I feed the same image to my, network. Okay. That was doing classification. I won't like my network to, suddenly start predicting that, okay, there is no tree now, right? So it is still a tree. It is just rotated. So it is still a image of a tree, but I have just rotated it. Okay. So this doesn't mean that there is no tree, in the picture. So, well, how, so this property is what we call as invariance. In particular, invariance to rotation. Or if I have to, elaborate it, what do I mean by, uh, invariance to a particular function is, let's say, if f is my function. Okay, and I want it to be invariant to some other function which is rotation. Let's say, let's call it r. So what I want is f of r of x is equal to f of x. Okay. So the way to read this is that okay, if a give for a given image, I have some output f of x. However, now if I rotate my image, or if I apply some transformation r to my image, and now apply my function to it, this output and the earlier output should be the same. This is what we mean by invariance. All right. We so I hope you get my point, right? Other thing that I would like this network to somehow accommodate is something called equivariance. What do I mean by now equivariance? Uh, so for example, now let's focus on the same example. So this example, right? Let's say that what I do now is I take this picture of this tree and let's say move it. So I take this picture and move it to something here. So let's say my image first initially my tree was here. Well, now my tree, let me see if I can do that. Right. So this is, yeah. So let's say yeah, something like this, right? Earlier, my image was something like this. The tree was sitting in the middle. Now what I did was, I shifted this tree to the right, and now my image looks something like this. Well, in this case, I still want my network to predict it to be a tree. I don't want it to, predict it to be something else. This is what I mean by equivariance, right? This is very similar to invariance, but there is a subtle difference. I will explain what it is. So let's say if I'm saying that my function f is equivariant to some function r, what I mean by it is f of r of x is equal to r of f of x. So how, the way to read this is, let's say I apply some transformation to my input x and give that as input to my function f. Whatever the output is, that output should be equivalent to applying my function f initially to my input and then applying this transformation r, right? So you can think of it as, let's say you are doing some sort of segmentation, right? One application, straightforward application of equivariance is, let's say you have some image and let's say you want to segment out something. So let's say you segmented out something, right? Segmentation basically means that there is, let's say you have a picture of a lot of balls and some background. You want to point out where the balls are exactly in the image. So let's say you segmented out this particular image, right? And you found that there is one ball and you segmented that part out of the image. Now, if I shift my ball to the left, okay, now my ball, okay, just a second. So let's say this was the original image and you segmented out something and you got this output. Now what you are doing is that, okay, you are applying some transformation R to your input image, right? And you are shifting this ball to the left. What you want, what you would like is you're applying this as well, okay? So this was what it was. What you would like to do, what you would like to, what you would expect is, you would expect your segmentation to be shifted by left as well, right? So let's say this was your R, this is your F, and this is also your F. So this is what you would like your, so if you see this path, you know, what is this path? This path is basically F of R of X, right? However, what is this path? This path is R of F of X, right? So this is what I mean by equivariance, that if something is shifting to the left, you want your output to be shifted as well. Something like this, right? All right. So these are the things that on a broad level, our human mind already accommodates, right? And we would like these things to be accommodated in a network as well. So out of these three things, CNNs actually incorporate two things. The two things are spatial structure and invariance. However, I would like to note here that CNNs, convolutional neural network, do not take into account equivariance. Okay, so this is something that I will leave up to you to ponder upon why convolutional neural networks are not good enough to capture equivariance. However, they can capture invariance and spatial stresses, right? All right. So all right. So having said all these things, let's see what exactly is convolution. Well, the I mean, uh, so so the way the first time I heard the word convolution was from. Okay, so let me write it down. Convolution. Right. The first time I heard convolution was from my signal processing course. Uh, okay, signal processing course. Right. So there what I saw was, so let's say you have some signal x of t, and you are passing it through a function which is, let's say, h. Okay, and you are getting some output y of t. Okay, something like this. Okay, so there is some in the chat. Okay. General maths concept. Can you please elaborate? I didn't follow. What do you mean by general maths concept? Uh, I don't know. Am I audible, or is there some issue? Is it a concept in mathematics applied to deep learning? Yeah, it is. Actually, it is. I mean, so convolution is something that is very widespread. I mean, I have seen it in signal processing course. I have also seen it in probability theory. Okay. So, however, I really don't know that what is, which of these two things first came up with the concept of convolution. But yeah, just like multiplication and addition, subtraction, and operations like these, convolution is a similar operation. You can look at it as something similar to multiplication and things like that. The way you think of multiplication operation, you can think of uh, convolution in a similar manner. Okay, it is an operation that takes into some two inputs and does something with them and gives something as output. Okay, uh, is that uh, is that what you were asking, or did I miss something? Okay, okay. So I was saying that the first time that I was introduced to convolution was in a signal processing course, and I was said that okay, if h is your uh, if I remember correctly, there was something called transfer function and uh, time equivalent of transfer function. I don't. So okay, let me write it down. Uh, okay, so let's say if h is your transfer function, but I am really not sure if this is called. I mean, I remember that transfer function is something in frequency domain, but I don't remember the exact term for the time domain equivalent. Was something else, but I don't remember exactly. Was it impulse function? Yeah, I think no. Okay, so okay, scratch that out. So let's say it's h is a transfer function. I mean, uh, any system given its can so if you are given any system which takes a signal as input and spits something as output, you can always find out the transfer function of that system. And the relation between y, h, and x is that y of t is equal to h of t, its convolution with x of t. So it's like the output is somehow obtained by mixing the transfer function and the input itself. Okay, and convolution is particularly very useful in signal processing, because mostly because in signal processing we generally work in the frequency domain, and surprisingly enough, this convolutional operation, when you go into the frequency domain, so let's say capital Y of S, this becomes H of S into X of S. So it's like simple multiplication in frequency domain. So if you have some background of signal processing, you would already know this. But if you don't know, it doesn't matter, because there is no need to go in detail about this topic. Okay. However, you can. I hope you can. So this was the first time I saw uh, probability theory, right? So I saw convolution in signal processing. The point where I saw convolution in probability theory was when I saw the formula for uh, density of a random variable, which is actually sum of two other random variables. Okay, so what do I mean by that? So let's say, so this was first thing. So let's say you have some random variable x, which is equal to x1 plus x2. Okay, and x1 and x2 are independent. They have, and x1, let's say, is sampled, has a distribution p1, and x2 has a distribution p2. So the distribution of x px is given by distribution convolution operation between p1 and p2. So this is another this was another point where I saw convolution operation in action. Okay, in particular, if you have two independent random variables, if I don't remember if they are identical as well or not, but I think so. No, I think not. But nonetheless, this is you can go and see sums of random variables, and this is a formula that you get. So convolution operation is very widespread. Okay, that is that is what I wanted to. That is what I wanted to convey. Now, but these things are, XT is basically a one-dimensional signal, which is, just which has just a single dimension. How does convolution look like in 2D? Well, the way convolutions look in 1D is as follows. So let's say you have a input X, okay? So this is your input X, and then you have a kernel, okay, which looks something like this, which is a smaller kernel, but it looks something like this. Okay, so let's say it has three inputs. So so this is your kernel K. So convolution between K and X is similar to taking a moving average. What do I mean by that? You take this kernel, okay, place it on this vector X. Okay, so let's do that. So I have taken this kernel, I have placed it here. Okay, now, so kernel will have some value here, kernel will have some value here, kernel will have some value here, right? Three entries. Similarly, your vector X will have some value here, will have some value here, some value here, right? Three entries. You do a dot multiplication of these two values. Basically, what I mean is, let's say this was x0 times you do k0, okay, plus plus x of 1 times k of 1 plus x of 2 times k of 2, right? So basically you just multiply these two values, this pink value and this blue value, and after multiplying them, add them. Okay, this is so, and now you apply this operation by moving this kernel to the right. So it's like you are taking this window and you are moving it to the, you are moving it towards the right, and basically the vector that you will, so this is like one output. Okay, so you are actually creating another vector. So you are actually creating another vector which will be a smaller vector. The first element of this vector will be this. Okay, similarly you will get the second input to this, third input to this, and similarly till the last input, whatever. So it's like there is a window You are moving this window on your vector, okay? You are multiplying it, and whatever the output is, you are putting it into a new vector, right? This is what convolution operation looks like. An equivalent operation for this in two dimension would be as follows. So let's say there is a 2D image now, okay, right? This is a 2D image now. So it only makes sense that if when your input was 1D, you used a 1D window, right? However, now since your input is 2D, it only makes sense that your window is 2D as well. So what do I mean by that? Now your window will also be a two-dimensional entity. That is all I'm saying. So what would it mean? So let's say that your input was earlier here. Okay. So uh, you did a dot multiplication as you were doing it here. Okay, like similar to this one. And you are now moving this kernel to the right, and eventually you will reach here. Now, after you are done with this row, you move to the next row. Okay, yeah, something like this. Again, you will move and come here, something like this. And similar way till you reach this point, right? Something like this. Okay, I hope you get the idea. I mean, it's difficult to draw on the tab. So this is what convolution operation looks like in uh, 2D. Okay. Now, when you might ask this question, well, does that take into account the spatial structure that I was talking about? Well, it does. How exactly? Well, let us see. So this was your image. Okay. Okay. Now let us consider this part of. So let's say at some point of time, your kernel was at this point, right? Now you can see that this was your pixel, okay, right? Well, or somehow because your kernel is two dimensional, it is not only looking at your this pixel, it is also looking at the neighboring pixel because it is two dimensional. Okay, I mean it is able to so its scope is not limited to the particular pixel that was earlier, this pixel. It is also having a look at the other pixels like this one, this one, so stuff like that. So, in some sense, at least we are guaranteed that using such a method will definitely take into account this inductive bias that we had. That the neighboring pixels also have some role to play in classification or any task that we can think of. Okay. Uh, so there are so the formula for so if you apply a kernel to a image, you will get some output as well. That output is generally smaller than the what the actual image was, and the I have taken this from the lecture slides. If you want to look at the ijth element of this, so as this, let's say this is your output. If you want to look at the ijth element of this thing, it is equivalent to looking at convolution of your image I with your kernel k and ijth element of that, which is equal to summation, this summation that is given here. But to be honest, I never remembered this thing till now. Okay, I just looked it up in the slides and I'm writing it here. I minus a, j minus b, k, e b. Okay, something. So this is what your ijth element will look like. So this is what your convolution operation looks like. So now I would say that I would appreciate you to go ahead and check. I will just write it here because if I go into this, we will miss the problem solving part, which I will start in just a second. Just check this thing that is convolution operation invariant. So I will appreciate you to just go and look this up, and also look if it is equivariant or I have already told you the answer. Nonetheless, maybe if you go and look it up, you will get a better answer to what I was trying to tell you. All right. So having said that, I will also refer you to one of the resources that I found very useful. Let me. Uh, how do I? Just a second. So there is a site which is called Pola dot uh, github.io. Okay. So this is a nice website if you want to mingle with CNNs and stuff like that. And there is one post regarding convolutions. Okay, this part, understanding convolutions, and this is a really nice blog written by Christopher Ola. Uh, I think he is in Anthropic AI. He's working at Anthropic AI. Earlier he was at OpenAI, and he actually explains that how convolutions are useful, and why it goes he goes beyond this trivial explanation that you want to capture the spaces structure and stuff like that. And it's a very nice read if you want to go into depth and get some really nice intuition. This is a must read blog. Okay. Okay. So you know all and all, so if you ask me that, okay, what is the broad benefits of using CNNs? Okay, the first advantage that I will say is that it's a very powerful way of describing uh, wiring of networks uh, to deal with input which have spatial structure. Okay, this is the first benefit. And the second benefit is implementational advantage. So I will just stop here. So if it is not clear why CNNs have some implementation advantage, you can let me know. But it was explained in the lecture as well, so I'm assuming that you know that. But if it is not clear, let me know. I will explain it nonetheless. Okay. So having said that, I think we could move on to the problems that are there. This week's problems are particularly easy. I mean, at least I felt that these were very easy. Uh, I I mean, if you have done these things, uh, if you have done these things, read the lectures and the notes, it will be very easy for you to solve these problems. Nonetheless, let's see what are these questions. Okay. Okay. So, is there any doubt? Maybe, I mean, before moving on to questions, if you have any doubt or any particular topic that you would like me to explain, I can go there. Otherwise, if not, I can move forward. All right. So let's move ahead. Okay. So the first question is: so which of the following 3 cross 3 kernels works best for edge detection? Okay. So we are given some options of 3 cross 3 kernels. 3 cross 3 kernels for edge detection, right? So we are asked that which of these options is appropriate for detecting an edge in an image. So the first option that is given to us is something like what 0 minus 1 0 minus 1 7 minus 1 0 minus 1 0, right? Something like this. Well, this thing, so I hope you know that negative values and smaller values represent you know dark, or from an image point of view it represents something which is dark, and this thing, if something which is relatively higher represents a bright point, right? So if you look at it, so this is actually like a, so I mean the way that total sum should be zero for edge detection. Well, not necessarily. So uh, so okay, let me come to that. Okay, let me come to that point. Okay, so this what this okay, let me just draw. Is there a black? So let me, okay, so this is what I know, something. Okay, so this kernel corresponds to something which is all black on the sides. Okay, something which is all black, right? And it has a certain bright spot in middle, like here. Uh, right? So if you plot this image, so consider this as an image. Okay, consider this as an image. The plot will look something like this, except uh, uh, okay, maybe I can draw something like this, right? These points are even darker. These points are even more darker. These points are even more darker. These points are even more. So I hope you will agree that so what I'm saying is that 0 corresponds to this color, minus 1 corresponds to the dark black color, and 7 corresponds to this white spot in middle. Something like this. So the question is, will something like this detect edges? Well, I mean, if you see, this won't actually represent an edge. The reason, so there is a mathematical reason that I didn't see in the lectures, to be honest. Okay, the reason is the following. So this is actually like a sync function. What do I mean by that is, so if you, so let's say if you look at this thing in 2D. Okay, so I'm some what I'm trying to say, I guess, is like, so let us say that you have an image. Okay, something like this is here. Okay, so 7 is a higher value. Okay, the the side parts are even lesser values, right? So they, so just let me maybe draw it something like this, which is going down. Okay, something like this, which I think I am doing this up, but yes, something like this, and there will be something like this. I mean, what I'm trying to say is that middle value is suddenly high. The edge values are suddenly very low, and the corner values are like in middle. Something like this can never capture a particular what do you call? It cannot capture a edge. If you want to, basically the, I mean, it's a bit difficult to explain. It's like intuition that is helping me here. But if you want to see if a particular filter can capture an but edge or not, just look at this figure that I'm showing you here. Okay, so does this look like an edge? Well, it doesn't, right? I mean, it looks like it doesn't look like an image, basically, right? So if a kernel's this uh, this image like something, So the corresponding image if, of a kernel, if it doesn't look like an image, it doesn't look like an edge, it will never detect an edge. So that is the idea. More specifically, this is actually like a Gaussian. So it's like on the top, it is having this the architecture of this kernel is such that it's having a very high value on the in the middle, right? And suddenly it has very low value in the boundaries, and on the corner it's like normal, right? So this is not a kernel that can be used to detect an edge, basically. That is like a very higher level intuition, but I feel that it requires some more in-depth explanation, which will involve, understanding what are low pass filters and high pass filters. Just explaining it like this is becoming a bit difficult for me. Okay, I think this type of question should not be there, but nonetheless they have put it. So I mean, I cannot argue on that. But yeah, right. Okay, coming to the next option, the B option. The B option is all zeros, right? All zeros. So I mean, I hope you will agree that if you convolve any, if this is your filter K, if you convolve any image with this image with this kernel, it will you will get an image which has all zeros. Okay, zeros. Why? Because let's say, I mean, you are essentially multiplying every element by zero, right? So the if you multiply any element by zero, the output will also be zero. So all you will get is zero. So actually, it won't actually capture the edge. It will what if even if there is an edge, it will give all black as output, which is not desired for edge detection. Right. Before going to C option, I would like to maybe go through the D option. So D option is all ones, right? All ones. Well, what does all ones filter? What will this all one filter do? Well, if so, it's like taking average in some sense. Basically, what you are saying is that okay. So let's say there is a big image. Okay, what you are saying is that there is, let's say there is a 3 cross 3 patch here. So let's say P1. This is P2. This is P3, right? And similarly till this is P9. Okay. So if I take this kernel, okay, if I take this kernel and put it here and multiply and see what the output is, I hope you will agree that the output will be P1 times 1 plus P2 times 1 till, P9 times 1 divided by 9, right? Something you will get this output. So this is like, this is similar to summation Pi 1 by 9, right? So basically, what we are doing is we are taking a bunch of pixels and taking the average of it. So this will basically make your picture blur. Okay, so averaging. So if you remember, if you have a noisy signal, something like this, and if you take this moving average, it has a smoothing effect, right? It will make your function something smooth. Similarly, taking using such kind of filter which actually averages your pixels is will also blur your image. There was one example in the slides as well where you actually saw that this is equivalent to basically uh, blurring the image. Okay, so this is also not good enough, right? So there is a C option which is the correct option. What does that say? So that option is interesting. It's all ones. Okay. It is all ones except at the middle. Okay. So what would this thing look like? So this thing will look something like this, right? So you have something in middle which is very black, very dark. Okay. Something like this. On the boundary, however, okay, maybe use some colors. Uh, On the boundary, however, it's all white. I'm representing it by yellow here because the background is already white. Something like this. Well, do you see something like this in edge? How does an edge look like? An edge looks like this, right? So edge and a particular edge looks something like this, something like something like this, right? So it's like saying, and more likely, it is saying that not only this, it will have black part here as well. Maybe I should do something like this. So if this is a, imagine that this is your image, right? This particular part is what you call an edge, right? So the question is, does a will an edge look some so will this be able to so does so so how does an edge look like? So if you look at this part here, right? If you take this thing and do a zoom up of this particular part, how would that look like? It will look something like this, right? So it's all white on the left. However, on the right, it's all black, and then it's all black, something like this, right? I mean, at least you will agree that this part is true. That on the left, it's all white. On the right, in the middle, it's all black, right? So the question is, can will something like this be used? Can something like this be used to detect this thing? Well, the answer is yes. It does work. Uh, why does this work? The answer given in the solutions is that it is saying that if you take, so this will be the response of this will be 0 if the neighboring pixels are so if the middle pixel and all the neighboring pixels are all the same, the response will be 0. However, for something like an edge, this is not true, and hence it will give a higher response. However, I somewhat disagree with this explanation. The answer that I would say is that uh, this filter is actually a high pass filter, okay, and uh, uh, an edge is also a edge is it is a high pass frequency thing. So it's like there is a rapid change in colors when you look at an edge. And since this is a high pass filter, it can detect a high pass entity. And edge, since edge is an actually an high pass entity, because how do you tell if something is a high pass entity or not? Well, the way to look at it is just look at it from left to right. Okay, so it was all white, 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 and suddenly it's black. So you are saying that the color has suddenly changed. So whenever there is sudden change, it reflects high frequency element, and hence a high pass filter can detect a high frequency entity, and that is why it can detect an edge. However, this was not taught in the lectures. At least I didn't find any explanation for that. So I'm not sure if this question should be there in the assignment or not. Okay, because uh, I feel that this question is not justified given that there has not been enough focus on these things. But I saw that at one place it was shown that this filter is used for sharpening. This thing I had seen, but nonetheless that doesn't justify why should it detect edge and things like that. So I'm not really sure that. Though the answer is correct, the explanation that is given is it's not justified. Yeah, so that is my take on this question. In particular, the question that you asked that okay, total sum should be 0 for edge detection. That is not true. In particular, if I take an image if I take a kernel which looks something like this, all right. So let's say it's 1 1 1, then it's 0 0 0 1 1 1, right? This will also ensure that you detect an edge. Okay, this is also edge detect. This can also be used for edge detection. Let's say you want to, so this will be used for edge detection for something like this, right? Something like this which has a horizontal edge. However, let's say you want to detect a vertical edge, then for that a filter something like this, right? 0 0 0 1 1 1 1 1 One, well, something like this will work. All right. To detect a bit rotated edge, you might use this one and stuff like that. So filters in itself is a vast topic. I will again uh, ask you to go through, maybe watch some initial lectures of this particular video playlist. It would be very useful to understand what I am trying to say here. Okay. So maybe if you have any doubt, you can ask me. I know that my explanation was not completely, justified, but given the amount of time it will take to explain all this high pass filter and low pass filter thing will be dramatically high. We'll miss out on the question. So if you have any specific question, maybe you can ask me. Okay. Uh, so if not, we'll move ahead. Okay. So the second question is that suppose we are given a 9 cross 9 image, okay, 9 cross 9 image, and we apply a filter C which has a 4 cross 4, it is a 4, which has a size of 4 cross 4, all right. What will be the dimension of the resultant image R, and we are given that stride is equal to 1. So remember the dimension for output of, so this is the formula that you should always remember. D out, the dimension of output, is equal to what? D in, the input dimension, minus the filter size, plus 2p by s plus 1. Okay. So 2p is the padding and f is the filter size, s is the stride. So s is given to be 1. Okay. So this is 1. D in is given to be 9. Filter size is mentioned to be 4. And since nothing is told about the padding, we will assume that the padding is 0 and plus 1, right? So what will this be? So this will be 9 minus 4 plus 1. This will be 6. Okay. So, so the width and height of, so since it is a 9 cross 9 image, the same formula will apply for height as well as width. So the output image will be 6 cross 6. Okay. So it's a simple question. I hope you will get that. Okay. If you didn't get it, let me know. So there's a third question. Uh, so there is a image that is given to us. Okay. So okay, let me. I won't draw the image, but I will write the dimensions. So there is 8 at the rate 128 cross 128 filters here. In the next time it's 8 at the rate 64 cross 64. So there is some operation that has been applied. Next time it is 24 at the rate 48 cross 48. All right. After that, we have 24 at the rate 16 cross 16. All right. After that, there is a flattening, which makes it 1 cross 256. After that, there is a simple linear feed forward layer, which makes it 1 cross 120. Okay, so overall, this is the overall structure. Okay. So let us look at the questions now. The third question basically asks us, what is the dimension of an individual filter in the initial layer? Okay, from going from here to here, what should be the dimension of the filter? Okay, and it is given that s is equal to 1. So the stride is always equal to 1, right? Okay, so let us again apply the same formula that we saw previously. So d out should be equal to what? D in minus f. Padding is given out to be 0, so let's not add that. Upon 1, stride is 1 and plus 1. Okay. So this is what we have. So we know that the output dimension is 64 here, right? 64. And input dimension is what? 128. 64 is equal to 128 minus f plus 1, right? So what does this mean? F should be equal to what? 128 plus 1 minus 64. So this will be 64 plus 1. This is 65. So this means that filter size at least should be 65 cross 65. How do we determine the number of filters that we have? Well, you just look at the number of output. Just look at the number of output. Uh, so the just look at the depth of the output. Okay, so it is 8, right? Now remember that each filter is responsible for one channel. Okay, there are 8 channels that are here, so there must be 8 filters, right? So the filter should have a dimension of 65 plus 65 plus 8. Okay, so and this will be the correct answer. So these are very straightforward questions. I hope you are seeing them. If not, if it is not clear how it is happening, then please unmute yourself or write in the chat box, and I will take the question. The fourth question asks you, how many filters are there in the initial layer? How many filters are there in the initial layer? We just answered that thing, right? That, if you want to see the number of filters, just look at the depth or number of channels in the output. It is given to be 8. Each kernel or each filter is responsible for one and only one channel. Okay, if there are 8 channels, that means that there must be 8 filters. So the answer will be straightforward 8. Okay, so this is again a very simple question. Okay, then there is the fifth question. If the dimension of the filter at max pull one layer, so this is the max pull one layer. Okay, if the dimension of filter max pull one layer is 33, so okay, so f the f is given to be of dimension what, 33 cross 33 cross 8, and the number of filter filter is 128. Okay, so and it is given that there are 128 such filters. Okay, what will be the dimension of the output layer? Okay, so whenever we have this type of question, it's very simple. Okay, what do we need to do is, so we know that the size of the filter is 33, right? If we know that, we will just apply this formula. D out is equal to D in minus F by 1 plus 1. Okay. So what is D in? Let us look again. So input had 128 size of width. Okay. So it's 128. Filter is given to be size of 33. So minus 33 by 1 plus 1. Right. So what will this be? 128 minus 33 is what? Uh, 128 minus 33. It's I think it's 95, right? 95 plus 1, it will be 96, right? So the output will have a dimension of what? Output will have a dimension of 96 cross 96. Okay. How many such filters will be there? As I said again, that each filter is responsible for one channel. There are 128 such filters, right? So we will have 96 cross 96 as 128. So there will be 120. It will have a depth of 128. Okay. Very simple question yet again. Okay. Coming to the sixth question. So this was fifth, right? Yeah. So coming to the sixth question. Sixth question is asking us, what are the new innovations used in Google Net that led to better results? Well, I mean, these types of questions are, these are like GK questions. I really don't, give them any weightage when I'm taking these questions. Like these are, you just need to remember there is no alternative to it. I mean, if you remember, if you have read the lecture notes and stuff like that, you would know that, there are two, three things that they did. First was, they used one cross one convolutions. Okay. They used so the second thing that they did was, as given in the option, they used multiple kernels, each with different different size. And third thing was, they were the first to introduce something called average boolean. So I hope you know what is average pooling. There are max pooling, average pooling, and stuff like that. So they were the first to use average pooling as well. So these are the three things that they did. This Google Net did. Okay. Uh, just remember, these are something that there is no logic to it. You just need to remember these things. There is no way to uh, I can justify, because even the research that I do involves a lot of heuristics. I try things, something works, something doesn't work. There is really no explanation for why something works and things like that. Okay, so just remember it, just like GK questions. Okay. Okay. Okay, moving forward. Seventh question. What is the seventh question? So you have been given two images. Okay, we observe that a neuron in third convolution layer of a CNN. Okay, which of the following? We observe that a neuron is in third convolutional layer of a CNN. Okay, which of the following statements is always true? Okay, so I hope you can see the images. Maybe you can open it in on your own screen and see what it is. So in first image, the open is written something like this, and the second image, and it is in a something like a square thing, and in the second image, it's again open is written. However, it's an oval thing, and which is in a square thing and something like this. Okay. All right. The question is, the neuron will fire again. So the first option says that this neuron in the third convolutional layer will fire again because both images contain the word open. Is this true? Well, I mean, we really don't know actually that if this will happen or not, because convolutional neural networks. I mean, I would say that not enough information has been provided to us to say that the statement is correct. It can or it may fire or it may not fire. We cannot say for sure. Similarly, the B option is will not fire, and the reason for this is the is color is different, because color is different. Well, again, as I said, that not enough information is given to us to say that if this is true or wrong, this is true or if this is false. C option is given to us, which says neuron will fire again since the background image will fire again. But I mean, so unless there is something very specific, we cannot say anything, because neural networks works in mysterious ways, and there is no particular explanation as to claim that if a particular neuron will fire at this point of time or not. So again, we cannot say if any of these statements is true or not. So in this case, none of these will be the correct option, because we cannot say the other options are correct or incorrect for sure. Okay. So this was the seventh question. Coming to the eighth question, it is saying that we have trained a CNN to detect dog faces. Okay, we found that CNN is good at detecting dog images taken in park, while it performs poorly on dog images taken inside a house. Okay, so if uh, dog images, image in park and dog image in room, so it is saying that it works good here, whereas here it doesn't work. Okay, we perform an occlusion experiment to inspect this phenomenon. Which of the following observations are most likely? Well, I mean, this is something that which is very interesting. Yeah, I will cover that question. The next question is that only. Okay, so just coming to that question. Yeah, so dog image in the park is basically the CNN detects a dog image that is in park. very in a very robust manner. However, it performs very poorly when the dog image is taken in a room. What does this mean? Is that somehow, let me write it down. Somehow, the network, the CNN, has learned a relation between park and dog. So it's like, let's say you have trained this classification problem on some data set, and the data set is such that you know uh, it has a lot of images of dog in park, whereas it has very less images of dogs inside a room. So by default, because your data is biased in such a manner, what it will learn is that it might learn to relate. So so it's like it might learn that, okay, dogs are where, if a park is there, then only there will be a dog. I mean, some it might learn a relation like that. So this is what we call as something called spurious correlation. It has learned a correlation between park and dog, okay, and this correlation is not good. That is all I'm saying, because parks and dogs are not related to each other. Like, dog can be anywhere, even if it is not a park, dog can be there. Okay. So if you perform an occlusion test, what you will see amongst the given options is that if you occlude if you occlude the grass, right? If you occlude the grass, you will see, uh, if you occlude the glass, there will be a large drop in performance. Why is that? Because of this thing that I just said here, right? That it has learned a relation between park and dog, and parks and grass are the same. So it's like, if you are saying that, okay, I won't show, if you don't show your network the park part of the image, okay, the greeny part of the image, the grass part, and only the dog part, it will basically perform poorly, because this is what it has been doing all the while. Okay. And the other options, are also incorrect. Uh, I mean, I hope that is clear, right? So this is what. So spurious correlation in general is a very serious problem in neural networks. The idea is basically because your data is biased, right? So for example, there was a recent event where this chat gpt, I hope you must have been listening about this chat gpt and all this stuff. So chat gpt is basically gpt-3, okay. However, there were earlier versions of gpt as well, gpt-1, gpt-2, and things like that. The earlier version, because they trained it on a biased data set, so there was some bias that was observed, that nurses. So the earlier versions of the gpt basically said that nurses are always women. Well, I mean, that is not always true, right? I mean, there can be male health workers as well in a hospital, which can do the job of a nurse and stuff like that. So because you trained your model on a data, so I mean, in general, in our society, we observe that nurses are generally female and stuff like that. Because the model was trained on this biased data, the model basically learned the same thing. Okay, that nurses are always female. However, this is not correct. Okay, so because you have some bias in your data set, you might encounter something called spurious correlation very frequently. Okay, and the spurious correlation that the network learned here was between park and dog. Okay, hence if you occlude the park part of the image, you will observe that there is a large drop in the performance. Okay, all right. So coming to the ninth question. So you have been given two images. Okay, we have trained a CNN. We have the pictures on the left, which when fed to a network as input gives a label as human. Okay, for the left image, the output is a human. Okay, and for the right image, the output is what? The picture on the right is the same as the same. Okay, it is left image plus some noise. Okay, some noise, eta. If we feed the right image as input to the CNN, then which of the following statements is true? Okay, so first option is CNN will detect human. Let me write down the first, all the options. P. CNN will detect will not detect human. Okay. C is CNN will uh, will detect a human, but with low probability. Okay. And D is insufficient input. So I hope this was the question that you were asking earlier. Well, the answer is okay. So I will just show you. So there is no information that we have been provided about this noise eta, right? So let us see if I can, construct an eta, if I can construct an eta which can satisfy each of these uh, options. Okay. So let us do that. So let's say I create a loss function L, which is equal to, let's say, let's say your network is f theta, right? So let's say just f, okay, don't include theta and all. Okay, so I'm saying that, let's say, so let's say there are two outputs of this network, f0 and f1. Okay, f1 basically says human, okay, and this says basically not human. Okay, all right. So let me construct a eta like this. Okay, so I'm saying that let my loss function be f of, so let's say the left image is just I. Okay, just let me use this I plus eta. Okay, f of I plus eta, and the zeroth part of it. So I'm saying the logit corresponding to not human part, not human. I'm saying that, okay, this will be the loss function, okay, and L of eta. Okay, so I am trying to optimize my eta. So I am saying that eta star, I will obtain my eta star as arg max over eta f of I plus eta and zeroth index of it. So what I am saying is that, okay, I will construct a noise eta. Okay. However, this noise should be such that when I add this noise to my original image I, okay, it should maximize the non-human logit. So there are there is some, so there are two logits at the output. Okay, so like there are some logits here, some networks here. Okay, so this corresponds to human, uh, and this corresponds to not human. Okay, so I'm saying that, okay, I'm adding, my eta is a learnable parameter now, and I'm saying that the eta should be such that the non-human logic should be very high. So this should be very high, is what I'm saying. Okay. So so I can always solve this optimization problem using gradient descent. I hope you by now you will agree with me on that, right? So such an eta, what will such an eta do? It will make this noisy image I plus eta, this new image, let's call it I dash, this will be predicted as not human. I hope you will agree with me on that, right? Because that is how I have constructed my eta. It should maximize the non-human logic, right? And if I add this noise to my image and pass it through the network, this will be maximum and this won't be as high as this is, okay? So it will predict non-human. So if I use this eta, right, this option which says not human is correct, will be correct, right? Okay, I hope you agree with me that on this. If this is not clear, just please ask me this, ask me the what is not clear. Okay, I will explain in more detail. Now let's say, so this was the first case, okay. In the second case, what I will do is I will say that my loss function is f of I plus eta. However, now this time I will take the first logic. What is the first logic? First logic corresponds to the human, okay. Basically, the network is detecting human, okay. This time, my eta star is going to be argmax of eta f of I plus eta. However, the first logic of it, okay. So what I'm saying right now is similar to this scenario where I maximize the zeroth logit of the network. I'm saying that now maximize the first logit of this network, okay? And the first logit of this network corresponds to detecting human, okay? So I'm saying that, okay, I will construct an eta by solving this optimization problem using gradient descent or whatever your favorite optimization algorithm is. And I will add this eta to my, so using, so if I solve this, and I use I plus eta star here, right? Let's call it I dash. This will give me human as a prediction, right? Uh, because I want my, because that is how I have trained my eta. That is how I have, obtained my eta by maximizing that particular logic. So it will predict human as output. So by this construction, this option is also correct, right? CNN, this time the CNN will detect it as human. Now let's say for the third option, right, this part, let's say, with low probability, right? So let's say, that I fix some uh, epsilon, which is much, much less than one, but it is greater than zero, right? This is possible, right? So it is, what I'm saying is that, so basically I'm saying that, okay, I am taking a very number which is very less in probability, okay? Okay. So now my loss function I'm saying is the following, that it is L f of I plus eta, the first logit of it minus epsilon, okay, the, let's say, the whole square of it, okay. However, I also want the non-human part of it, non-human logic, to be less, right? So if I have to minimize this, I will also minimize f of I plus eta, zeroth part of it, right? This is what I'm saying. So, so if I obtain this time, if I obtain my eta star, which is arg min of eta, L of eta, right? So if I solve this optimization problem, right? So what should happen is this part should be equal. So this part will be, the least value of this part is what? Zero, right? When is that possible? When my f of I plus eta and one part of the first index is equal to epsilon, only then this can be zero, right? So okay, so now what is happening is my network here is outputting epsilon as output. Okay. However, I'm also minimizing this thing, right? So what will be the minimum value that it can take? It can be any arbitrary value, right? Something like -10 it can take, whatever it is. Well, now this time, if I use this and I take I plus eta star and call it I dash, the output of this will still be human, but with what probability? Here with probability epsilon. Now epsilon was very small, right? So it was so with very low probability, with epsilon probability, which is very low, CNN is predicting it as human, right? So well, I mean, by this construction, this option is also correct. So the way I construct my eta, okay, so this was the third option, right? Yeah. So the way I construct my eta, so I showed you three ways to construct eta: first, second, and third. Each of these options can be satisfied, right? And hence, I mean, we are not, so what we can say is that we are not given sufficient information to tell anything about the above options, basically. All right. So insufficient so the information provided is not sufficient to say anything. Okay. Let me know if there is some doubt or you didn't understand something. The 10th question is basically asking you which of the following architectures has highest number of layers. Well, this is again like a GK question, okay? So you need to just remember that ResNet amongst these, ResNet has the highest number of layers, and hence that is the correct option. So again, I mean, there are some GK type of questions uh, in this in this assignment. So you just need to remember it. There is no alternative to. All right. So so this was basically the assignment. The assignment was more or less easy. That is what I felt. However, the first question, the way I feel that there is no sufficient information that is provided in the first question. I mean, the one can answer that to the first question. However, it is not taught in the class is what I have felt. But it was told in a very hand wavy manner. Okay. Okay. So Ram is asking that I have a general query. Is difference between classic supervised machine learning and supervised deep learning is that in ML we know f of x, y is equal to x plus b, and learning is around finding the parameters of f of x and try to fit around the data. In DL we don't know f of x but try to learn parameters to derive output based on given data. Well, actually that is a good question, but the answer is that both of them are more or less the same. The only difference between ML, machine learning, what you are calling, and DL, the deep learning that you are calling, is the difference of back propagation. Okay, I mean, deep learning, you can have a lot of parameters, and you can learn those parameters using gradient back propagation and gradient descents as such. However, in ML, it's not about just you knowing the form of function. If it is ax plus b or something, there can be at any form. I mean, there is no such different. You cannot actually so for example, let's say the thing that you are asking, that y is equal to x plus b, right? So that isn't it equivalent to let's say x is your input, and there is, so let's say this was your x, okay, one vector x, and then you are saying that there were several inputs here, and you are saying that now you have to give me one y, which is what this is, a w matrix, okay, w matrix times x plus some bias term b. So this is, doesn't this resemble a neural network, right? I mean, this is also you can see it as a deep learning thing, right? In a similar fashion, you can see look at deep learning theory as classical ML and stuff like that. There is no distinction between these two. They are both the same. It's just that deep learning has a lot of hype because you can actually use back propagation to learn a lot of parameters. That's the only difference in my opinion. The rest of the things, there is a lot of interplay between what you are calling as ML and what you are calling as TL. Okay, there is no proper differentiation between these two. Is that clear, or was I not clear? Uh, if you have any doubt, further questions, or anything. By the way, I also saw that last assignments question, there were some doubts that you had that got rectified. I also felt that those should have been rectified. So I hope you are happy after that. Okay. So maybe if you don't, if have any questions, either we can stop, or if you have any further questions, then we can take it up. Let me know if you have any other further questions. Okay. So if you don't have any further questions, maybe we can stop the recording and stop the recording. Yeah.